You ever look at an equation like a plus b raised to some ridiculous power and just think, nope? Well, today we're going to tackle that head on. We're demystifying binomial expansion, and you're going to see that behind all that scary-looking algebra, there are some seriously cool and simple patterns. So, here's our game plan. We're going to start with the absolute basics, like what even is a binomial? Then we'll check out our first awesome tool, a neat visual trick called Pascal's triangle. From there, we'll level up to the binomial theorem itself. And finally, we'll get our hands dirty and see how it all works with a couple of examples.
Right, first things first, before we can expand anything, we've got to be crystal clear on what a binomial actually is. Let's build a solid foundation.
I mean, let's be real. Seeing something like this probably makes you want to just close the book. You could sit there and multiply 2x plus 5 by itself over and over, but man, that's messy. And there are so many places to make a tiny mistake. We're here to learn a way smarter way to do this.
So, let's meet the star of the show, the binomial. It sounds fancy, but it's super simple. Bi means two, right? Like bicycle. And nomial just means term. So a binomial is just any expression with two terms squished together. That's it. Stuff like x plus 5 or 2a minus 3b. These are our building blocks.
Okay, now for our first secret weapon. Instead of grinding through all that multiplication, we can use this beautiful visual pattern that basically hands us the answers. It's time to meet Pascal's triangle.
You know, building this thing is actually kind of fun. You just pop a 1 at the very top, then every new row you make, you put 1s on the outside. And the magic is what happens in the middle. Any number inside the triangle is just the sum of the two numbers right above it. See? 1 plus 1 gives you 2. 1 plus 2 gives you 3. You just keep going like that.
Now here's the trick. Each row of that triangle gives you the special numbers, the coefficients, for an expansion. So if you're raising something to the power of 3, you find the row that starts with 1, 3, and there are your numbers. And the variables? They do this perfect little dance. The first term's power counts down from 3 to 0, while the second term's power counts up from 0 to 3.
Here's a kind of silly but helpful way to remember the powers. Just imagine you have a total power of n. For every single term in your answer, the powers of a and b have to add up to n. It's a perfect trade-off. If the power on a drops by 1, the power on b has to go up by 1 to keep things balanced.
Okay, so Pascal's triangle is really cool, but it has a weakness. For the really big jobs, we need to upgrade our toolkit. It's time to bring out the heavy hitter, the binomial theorem.
I mean, just look at this thing. Expanding something to the power of 25? Are you seriously going to sit there and write out 26 rows of Pascal's triangle? No thanks. This is where our triangle trick just isn't practical anymore. We need a formula, a direct route.
And here it is, the binomial theorem. Now, I know it looks a little intimidating with all those letters, but this formula is the ultimate tool. It lets us figure out the expansion for any power we want without drawing a single thing. It's like a calculator for each and every term.
The real engine running this whole formula is this little piece called a combination. It's how we find those coefficients. And not exclamation point, that's called a factorial. It's just a shorthand. So 4 factorial, or 4i, just means 4 times 3 times 2 times 1. This little formula right here lets us find any number from Pascal's triangle without ever having to draw it. All right, enough with the theory. The only way to really get a feel for this stuff is to see it work. So let's tackle a couple of problems, one with each of our new tools. Okay, for our first one, we're expanding 2 plus 5x to the third power. Now, since the power is small, it's just a 3, Pascal's triangle is the perfect choice. We just look at the right row and boom, our coefficients are waiting for us. 1, 3, 3, 1. Easy. And here's how it all comes together. We just lay out our coefficients. 1, 3, 3, 1. Then we do the power dance. The first term, the 2, goes power 3, 2, 1, then 0. The second term, the 5x, goes power 0, 1, 2, then 3. After that, it's just careful math to clean it all up, and we get our final expanded answer. Okay, now for the boss battle. We need to find one single thing, the coefficient of the x to the 20th power term in the expansion of 2 minus x to the 25th power. Yeah, Pascal's triangle is not going to happen. This is a job for the binomial theorem. So using the theorem, we can build the exact term we need and ignore everything else. The total power is 25. We want our second term, negative x, to have a power of 20. That means our first term, 2, has to get the leftover power, which is 5. So we plug those numbers into our combination formula, 25C20, and it spits out that huge number, 53,130. We're not done yet. We take that massive coefficient and multiply it by 2 to the 5th power, which is 32. And the final number in front of x to the 20th is 1,700,160. Could you imagine trying to find that with a triangle? No way. The theorem is like a surgical tool. So, what's the big takeaway here? It's simple, really. You have two tools, and you just have to pick the right one for the job. If you've got a small power and you need the whole expansion, Pascal's triangle is your best friend. It's fast and visual. But if you have a huge power, or you just need to find one specific piece of the puzzle, the binomial theorem is the only way to go. And this isn't just some abstract math problem. This kind of expansion is a huge deal in probability, in economics, all over the place. It's a perfect example of how a very simple starting point, just two little terms, can explode into this massive, complex, but totally predictable pattern. It kind of makes you wonder, right? What other simple patterns are out there, secretly running the show?